I'm here today to talk about a tool that we developed. It's called Liaison. The title of the paper is actually an open source tool for distributed co-simulations. I wanted already from the beginning to put in the geo-distributed here, but I lost an argument with one of the co-authors, so we went with only distributed simulations. But now, since I'm holding the presentation, we're going to focus on the geo-distributed part of it. My name is Fredrik Olsson, and as Christian said, I'm a research and development engineer at RISE, located in Gothenburg, Sweden. I wrote this article together with two of my colleagues, Luis and Jan, and we're all working at the maritime department at RISE. All right, so for the agenda, I've deliberately kept this a little bit according to how you would outline a specification document in software development. I want to focus on the why and the what and the how, and then we'll finish off with an example showing off how this can be used and the drawbacks and so on. All right, now some of you probably have ventured into distributed co-simulations before. You're here because you're interested in this, and perhaps on some of your minds you're thinking this. All right, this is yet another proxying tool for FMUs, right? There are different tools existing for this and so on. So one of my goals today is to try to explain why we needed yet another tool. Moving on to the why, and I guess that everyone knows what FMI is because you're here. But essentially, it's a set of interfaces and then conventions for how to share models in terms of package code, right? We encapsulate the models as functional muckup units, and then in theory, these can be shared so that we can create simulations in different constellations. In practice, however, there are lots of factors. I've listed a few of them here that are perhaps the most common ones that sometimes make sharing of the physical FMUs, or not the physical one, but the file-based FMUs unfeasible. We have portability issues. You have FMUs that are built for certain architectures or for certain operating systems and so on. They're not compatible with the recipient's architecture or operating system. You also have intellectual property issues. You have lawyers saying that, well, you're not allowed to share this outside the house. You may have other concerns regarding sending off an FMU in a file-based way to somewhere else. You don't really know what's happening with those files once you've sent them out of the house. The recipient on their end might send it to someone else, and then it's out. And as a recipient of an FMU, you don't really know what it actually contains. I mean, you're trusting the one that builds the FMU that it contains what he or she says that it contains. So you don't really know what's actually inside. And these are all kind of the typical solutions of this is you distribute the co-simulations, right? You distribute it. And I'm going to move on to the case that we wanted to solve when we started with this was actually this approach. This is what we wanted to in the end have a solution for. So our office is based in Gothenburg. We have, at that point, we had a collaboration with a client in Paris, and we were interested in running co-simulations together with them in different setups. At that point, particularly for development of certain aspects of a software solution, and for different reasons, both the ones mentioned before and other reasons, we decided that the best setup would actually be that we keep our code in-house at our place, they keep their code in-house at their place, and then we try to run the co-simulation in a geo-distributed fashion. That would be the best approach in terms of a lot of issues that we had. Then we figured, well, I mean, we know that there are a lot of things, there are a lot of tools available in the FMI ecosystem. Surely this should be an easy problem, right? And we looked around. We found existing proxy tools. This is a FMU proxy, which is a really nice tool for setting up distributed co-simulations. There's a UniFMU, which works in a similar way, also very nice for setting up distributed co-simulations. You have the layered standard, the distributed co-simulation protocol, and you have some implementations of that one. And those are all very nice. Our problem was that in one way or another, they all work approximately like this. You have a server and you have a client, right? Someone needs to initiate the connection between those. Typically, it's the client. The client initiates the connection. Once the connection is initialized, you can start sending function calls across. This is what the typical distributed co-simulation setup looks like. Now, when we want to do geo-distributed co-simulations with this, we face two additional issues that are, well, the connectivity. How is the client able to connect to a server that runs somewhere far away? If we have a client in Paris, a client software in Paris, and that client software wants to initiate a connection to a server software running in Gothenburg. How do we do that? And secondly, security. How do we make sure that all the communication that happens between the client and the server software is kept secured throughout the co-simulation? Maybe we have. I mean, if we're not okay to share the FMUs in a file-based approach from the beginning, then probably we're not okay with sending stuff without encryption across the internet either. So those are our two main problems here. And then we started looking into, all right, using the existing tools, so the FMU proxy or the DCP-lib or so on. We have two options of how to deal with this, essentially. We have either we need to open ports in some, preferably at the server location. We need to open a port in Gothenburg so that we can actually have a well-known address to point the client at. This is where you should connect. That solves the connectivity problem, but then you also need to add security measures on top of that. That could be encryptions like the TLS encryption or whatever. The other approach would be to set up a full-blown VPN setup, so a virtual private network, so that we can act as we configure a separate virtual private network just for the co-simulation setup. That's perfectly doable. It still requires us to have a well-known address so that someone can initiate the connection, or all the nodes can initiate the connection, and it requires quite some configuration on all endpoints. So we kind of, if we want to do it that way, both us in Gothenburg and our clients in Paris must be okay with setting up a VPN connection. The positive side effect of the VPN is that you typically have the security measures included, right? You get that for free. Well, these are workable solutions, but they're quite finicky. It takes quite a lot of networking knowledge, and it takes quite a lot of setups. You need to probably need to involve the IT department at your place and so on to set these things up, and it's a hassle. So we thought, let's try to do something about this. And now we get to the what. And we created Liaison, which is a new open source tool. It's a command line interface designed to address the typical challenges related to distributed co-simulation, such as portability, security, and intellectual property when sharing functional muckup units adhering to FMI 3.0. We are focused on FMI 3.0 for now. And we said that, well, it should act as an intermediary between the original FMU, which should stay in the original location, and the simulation engine, or the other part of the simulation, which could be at another geo-distributed location. and we wanted to be fully, we wanted to be able to simulate fully geo-distributed setups, but with a minimal network configuration. We as simulation engineers, we don't want to hassle with VPN setups and so on in order to get things to work. And perhaps what I should say is that this kind of venture already from the beginning it's not, I mean, the DCP standard, for example, it's typically relating to or it has a lot of writings about real-time applications. You wouldn't do real-time simulations across the internet, for example, between Gothenburg and Paris. That's not really the case. This is typically for running co-simulations that are just you want to see the end result at some point. It doesn't really matter if it's we don't have any hard or soft real-time constraints to adhere to. All right, back to this. So then, next part of this presentation is we're going to go through the how. How did we do this, and what does it look like? And this is essentially the same thing that FME proxy and UniFMU already does. Both them and we take an original FMU, and then we kind of split it. We couple the original FMU with some kind of server software, and we create a proxy or a liaison FMU. That's basically an empty shell mimicking the interface of the original FMU, but it acts as a proxy for proxying those function calls over the wire to the liaison server and the original FMU. So essentially, well, this is typically how all the distributed co-simulation solutions function these days. And so the interesting part is, well, in order to enable the geo-distributed part, we need to be smart about the red arrow. How do we do the communication? How do we ensure connectivity? And how do we ensure security? Since FMI is typically a function-based protocol, or function-based interface, it lends itself very, very well to something called remote procedure calls, which is essentially function calls across a wire. You serialize the function parameters and the function response, and you send it over the wire. So that's also it's the typical approach. The new part here in Liaison is that we have opted not for typical network transport protocols such as TCP or UDP or 0MQ, but we have actually adopted a transport protocol called Zenoh, which is something that's developed primarily perhaps as a communication middleware targeting automotive businesses for intercommunication in the vehicle between different types of sensors and processing units and so on. But as we'll see, it lends itself quite well to this as well. And in brief then, probably, I don't think many of you have heard of Zenoh, maybe some. But it's a publish, subscribe, query protocol. It describes itself. So you can publish data, you can subscribe to data, and you can query for data, which is, you could say it's a generalization of an RPC setup. And one of the interesting features is that routing in a Zenoh network is defined not by the hosts themselves, but it's defined by a key space. We'll see more about that soon. You have many available transport protocols that Zenoh uses. You can use it over UDP, TCP, you can use it over QUIC. WebSockets, Serial, Unix, etc. And you have security features out of the box. This is to show how this is a graphic borrowed from Zenoh, and it shows how it's routing traffic using key spaces instead. You see these are key spaces, the gray text here, instead of the actual IP addresses or host names of the different nodes. All right, networking with Zenoh. You have peer mode, which is peer-to-peer. Essentially, everyone talks to everyone. You have client mode, which is server-client. And you have something called software routers, which can act as an intermediary so that the two nodes don't need to have direct contact with each other. All right, so how about geo-distribution with Zenoh? We can do it the typical way. You can set up one node in Paris, one node in Gothenburg, and you can do it the same way as we tried to avoid from the beginning. So that's not really a good way of doing it. But we can also utilize this thing with software routers. So what we've done is that we set up a software router. It's a one-time setup somewhere at a well-known address, and then any number of nodes can connect to that well-known router for connectivity towards any of the other nodes that are connected to that router. And this lends us to, with possible setups using Zenoh, is you have the typical one. Well, you have one setup, obviously, that are in a single computer. You have a simulation software, Liaison FMU, Liaison server, and FMU. This is not really, I mean, typically you would use, I'm not going to be able to finish this, I see. All right, let's skip this part. And then we go into the example. I think this is, for this, running it in a single environment, you have zero configuration. Running it in a single local area network, you have zero configuration. And running it across a wide area network, so essentially across the internet, requires minimal configuration. It requires some configuration up front, but then the node n+1 requires zero configuration. We'll move on to an example. This is a typical, we'll skip that one. This is a typical example. We have a co-simulation engine. We have in our case, since we're dealing with maritime stuff, we have a vessel FMU and we have a controller FMU, and we want to connect these ones. We have a bunch of different scenarios, a reference scenario, a local scenario that runs on a single computer, a LAN scenario that runs on a single local area network, and a WAN scenario that runs across the internet. And we run this for several different communication step sizes. 0.1 says 0.1 second, 1 second, and 10 seconds. And this is what it looked like. So for 0.1 seconds of communication step size, well, you have a large penalty for running it across the wide area network. The execution time is like 7 or 8 times larger than running it locally. So that's not really a good fit. But already for communication step sizes of 1 second, the gap is not that big, essentially. So yeah, I think that's the interesting part to get from this picture. And so in conclusion, we can say that, yeah, we found a way of dealing with geo-distributed co-simulations. That's Liaison with either zero or very minimal configuration. For the WAN connections, we require some upfront configuration, but the one extra node requires essentially zero configuration. And the overhead introduced by Liaison in terms of communication it's there, and it's heavily dependent on the communication step size, as expected. But since this is not for real-time simulations, it's not. I mean, it's something that you need to be aware of, but it's not a deal breaker. And right now, this tool only supports FMI 3.0. And only a subset implemented so far. So that's something that we'll continue to work on. We're thinking about also adding support for FMI 2.0. We'll see about that. And this has mainly been used so far for our internal and our clients that we work with. So it's not been tested with all different various simulation environments. Last, I just want to point out that this work was carried out as part of a Windship project funded by Swedish Transport Administration's Industry Program Sustainable Shipping, led by Lighthouse. And that's it. Thank you. And this tool is available on GitHub. So feel free to have a look, contribute, whatever. Thank you.